So I've been with NVIDIA for just about 3 years, actually. I think it was 3 years, about 2 days ago, actually. And I actually wear quite a few hats. This is one that I'm most proud of. If you walk backwards that way, you will see the Intel-sponsored NASA Frontier Development Lab booth. It's really fantastic. Go and see them. We're here in the lab to live stage, and this really is the epitome of going from lab to live as quick as possible. NASA FDL, or Frontier Development Lab, is essentially a research accelerator. We take some of the world's biggest problems. This is planetary defense with NASA, so asteroid detection, solar storm prediction. Take some of these huge humanity-sized problems and condense it to a TRL, tech-ready level prototype within 8 weeks. We started with 6 weeks, but then we figured maybe another week for everybody to meet each other at the beginning and a week at the end. So this is really cool. Take a look online and get involved if you want to. This year, we actually spread even further around the globe. So FDL is now in Europe, hosted by the European Space Agency, and their focus is Earth observation, which of course is huge amounts of data analytics. And NVIDIA is very proud to be founding partners. So we're also very, very proud of our gaming roots. NVIDIA started out as this very, very agile company, and I think this is our major advantage in this AI arena. Essentially, we have grown from there. We clearly have a lot to do with artificial intelligence now. It's a huge industry, but also the transportation industry as well. And I'll get into that in a little bit more detail. This is really our bread and butter, though. To understand the huge amounts of data that we currently have now needs visualization. So what we're actually starting to see is the beginnings of a full simulation of a supernova. This is over a terabyte of data in 1,077 time steps. We have to do the compute on NVIDIA's GPU. We also have to provide the visualization, the rendering of this huge space. Something as profound as a supernova, how could you possibly understand this on think of the reams and reams of white paper that we used to look at time series data. We cannot possibly understand that, so we need the visualization side of it. And this is essentially our bread and butter. Now, AI itself has actually had quite a rocky road. This is yet another, I don't know if you can see this properly, but this is yet another free course that you can go online and do. Intro to Deep Learning from MIT. We actually guest lecture in this course on self-driving cars. But what it's actually portraying is the AI winters that this technology has actually gone through. And the explosive growth that you can actually see after the second AI winter. Around, I don't know if you can see that, I can't because of the sun at the moment, but around 2012, this is what the scene looked like across the AI research field. Today, this is what the scene looks like. This explosive growth, or as our CEO likes to call it, the Cambrian explosion. These are just neural network architectures. And it really just goes to show that we're now definitely in what we like to say is the era of AI. And this is across the board. It's not just the Twitters and the Googles and the Facebooks so far as web services, but it's also self-driving cars, or SDC, and across the board intelligent machines. Obviously SoftBank is the main sponsor here at CogX. Go and see some of the robotics that are going to be on display here. Healthcare, this is where I actually started out. And security, here we're looking at the whole smart city arena, essentially. It really is very, very profound. And the reason we are seeing this explosive growth is because of the applicability to us, to humans. We now have so many applications But these applications are what is known as narrow AI. And this is really, really important, that you basically don't get pulled into the hype of the movies and the killer robots. We are nowhere near artificial general intelligence, but we are on that road. That's the path. And this explosive growth that we're seeing will actually take us there. So don't believe the hype. Don't get caught into it in too much. Concentrate on the research. And there is a phenomenal amount of research. It's something like 80 papers a day are being published onto the archive website. So concentrate on this as we do. We actually put a lot of time and investment into our own research arm. They're actually based in Santa Clara, which is our headquarters, as well as Helsinki, and then also dotted around various spaces. So it's really important that you concentrate on this and don't get too much into it, because this is essentially what we are trying to produce artificially. This is an 1865 drawing of a human cell with the soma and the dendrites. We are essentially trying to reproduce this, and we're trying to reproduce it with the knowledge that we actually have of our own biological systems, our own brains. And there is now it's a convergence essentially between neuroscience and computer science. And we're learning massive amounts from both sides. It's really, this has a lot to do with the actual progress we have. And don't forget why we're actually doing this. This is to augment ourselves. This is not to take jobs. It is essentially to make us better at what we're capable of doing. And it's really, really important on the application side, when you talk about projects that you're actually going to be looking at, to make sure that you are not being too disruptive of the current human skill sets. There are many, many projects around that have to be understanding of our capability and to simply make it better with AI. The disruption is twofold in that sense. You have to put a lot of effort into enhancing what we can do. Now, getting back to deep learning or the AI side, there's actually two main workloads. One is the actual training side, when you're talking about supervised learning. Most of the AI systems that you will have heard about or understood, even to a certain extent, is supervised learning, which requires a lot of data or the equivalent of experience. And it is the ingest of that data into the AI system that makes it computationally intensive. The inference part is actually very low on the computation side, but it is hard, and I'll get back to that in just a minute. But from a project basis, this is a really great book. It's Andrew Ng's latest book. You can actually just go to mllearning.org and download the full book. But it is very easy to read, and it's based on project applied deep learning. So take a look at that. Now, essentially, I mentioned about the inference, but we actually deal in compute from our credit card size Jetson embedded devices right up to massive hyperscale data centers, which are essentially the most complicated computers that we have ever built, we as a society. So the Summit US supercomputer just went online. This has a staggering number of GPUs, and it's capable of 3.3 exaops. So that's a billion operations per second. It's really phenomenal. But the actual inference side of producing at scale results is quite difficult. So Plaster is something that our CEO came up with just to try and remember all of the different facets of getting inference: programmability, latency, accuracy, size of the actual model that you're using, throughput, energy efficiency, and the rate of learning. These are all things that you have to think about. And the other thing as well is AI is just code. If you have a good crack team of coders, you are halfway there already. This is really, really essential. Get a team together with some good coders. And this is pretty much, a job well done already. a lot of people get surprised by this, but AI really is code. If somebody is comfortable with the code, then they can utilize a lot of the shared resources. That is the reason that AI is so profound in its progress today. So this is essentially how we learn. Reinforcement learning is the next stage on from supervised and unsupervised learning. This is where the really profound stuff has come about, things like AlphaGo, for example. And it's simply this constant use of the world around us. And it's really, really important, both in a virtual sense as well as the actual physical sense. So this is some work that I was doing. I was coding up a virtual KUKA robot, 6-joint KUKA, for the National Nuclear Laboratory back in 2013. There's no AI in this particular project, but basically what we're trying to do is prove a safety case for nuclear decommissioning to have some kind of semi-autonomy. So all you do is you literally use SolidWorks to pull in a CAD model. Here it's a 6-joint KUKA. You can use things like Blender to put in the centers of gravity, and then you hook the whole thing up, in our case, to an Xbox controller, which had limited degrees of freedom, but it was enough to actually prove a safety case. The National Nuclear Laboratory then went on, and within nuclear decommissioning, we now have fully autonomous robots in only a matter of 5 years. It makes a difference using a virtual world because, for example, Boston Dynamics, this, I'm not going to bother running the actual video, but we've, whether or not you've seen this before, this is their Atlas machine just essentially going for a run. Now, back in 2016, I believe it was, Boston Dynamics brought their Spot Mini. Have you seen that, the dog that's all over YouTube because they kick it and push it over and things like that? So Spot Mini at the time went on stage at the biggest AI conference that there is in the world today with no AI whatsoever, and I've never seen the kind of response before from 6,000-7,000 AI researchers. But at the time there was no AI, and I spoke to Mark Raybert then and said, are you planning on doing this? At the time they weren't, but Spot Mini now has autonomous navigation. At the moment Atlas is purely mechanical, but the real power that comes from using virtual environments is the learning that you can do in massive parallel lines. Here we're essentially, each of these are virtual agents that are not only learning to run but to behave as they're actually walking around and bumping into things. This is actually a screenshot from my colleague Hamad's VR headset. He's actually in our virtual environment, something that we call holodeck. We actually designed this environment just to look like a cute nursery, because what Hamad is doing is he's using reinforcement learning to teach and to play dominoes with this virtual robot. Once the robot, and it's using two separate neural networks to actually learn this, a policy and a value network, once the robot's sufficiently trained, you can then simply port it into a real robot. Using simulation for the training and then deploying, and with this continuous circle that is this world that we live in, this dynamic world. Here, basically, the robot is learning how to simply, using reinforcement learning, get the puck into the basket. And he's starting from scratch. Reinforcement learning is literally start from scratch, start from random movements, and you get a scalar reward for actually hitting your objective. Now, this is obviously very, very slowed down, but we could have thousands of these virtual PR2s doing the same thing and actually optimizing and doing self-play against them. Most of the actual work from AlphaGo was due to self-play with thousands and thousands of virtual robots. Now, once you've actually trained this system, you can then just simply put those that set of weights into a real robot and deploy. And it really is as simple as that. Now, we've actually been working in this space for quite a long time. We developed holodeck because we were working with car manufacturers. And this is something within holodeck where we can now essentially, it's not just a case of being able to put AI into a virtual environment, but we can use it for all sorts of ways. Now, in this place, this was actually demoed at our main conference in Santa Clara in March, where we actually take the car itself. We have somebody on stage in a full VR kit. They're able to actually drive the virtual car, which is driving the actual real car. Now, the applications for this abound, and we're only just playing in this space. So if you have some really great ideas, let us know. We can give you access to this kind of environment, and you can play and go from lab to live really, really quickly. Because what we're essentially trying to do is bring together this entire system, which is end-to-end for AV or autonomous vehicles, not necessarily just cars, but any autonomous vehicle. This is Waymo's Carcraft. They are capable of putting hundreds and hundreds of different cars or agents, virtual agents, driving billions of miles a day. It's been estimated that we would need to cover something like 11 billion miles just to get one self-driving car performant today. But the real problem with that is, how do you scale? How do you compute that incredible amount of data? Luckily, and this is the AI world that I'm very, very proud to be in, we share data. So Berkeley Deep Drive just open sourced another data set. This is a huge data set of videos with labels. You can just go here to the website and actually download all this data and start playing in this arena. The other thing is that we never stand still. NVIDIA always adapts, and we have to, okay. So we essentially designed our own chip specifically for the transport industry, but it's actually an ASIC, an application-specific integrated circuit, and the application is deep learning. It has a lot of different components, and on there is a deep learning accelerator. We actually just open sourced it. You can just go to this website now and take all the specs and actually go ahead and use it. What we're trying to do is essentially turn what is today, currently, the boot of a self-driving car into a much more optimized. We're essentially full stack performance optimizers, and that includes the self-driving car. There's also a Jetson version. So I mentioned the credit card sized embedded GPU that we have. This is the Xavier version of it. It's capable of 30 trillion operations per second at only 30 watts. And the Jetson Xavier, there's a lot more behind it. I need to run through because I've only got a couple of minutes left. But the software that comes with it, with all of this, all of our software is actually free. You just sign up to actually access it. TensorRT is about making inference about as easy as possible. And we've done all the hard work for you. Very quick demo here. This is a neural network that's been trained to understand every single flower that there is. This is a video running on CPU. This is a video of the actual inference capable when you bring GPUs into the equation. Here we're able to calculate about 911 images per second. And this is when you actually incorporate our optimized software, TensorRT, and you can just download this now. We've done the hard work for you. Don't take my word for it though, RoboRacer here. All of their units use our Drive PX2 driving platform, so go and talk to them about it. And really, this entire ecosystem has been built for you, from the massive infrastructure right down to the actual nanometer. So this is us optimizing PCIe, PCI Express. And again, when we brought the new chips in, Pascal, and then our latest card, which is Volta. Essentially, NV Switch is the fastest we can get. This is 5 times the performance of PCIe, and we need to do this. We need to do this simply because I'm getting told I have to go now. But essentially, we need to do this because this is our latest offering, which is 16 GPUs in one unit with all of the software. When you have 16 different GPUs, you have to get the capability. I need to quickly run on now. Within that is all the software. You can just access this to keep it up to date. I'm completely out of time now. There is a lot more information to be had. Just go online to our Deep Learning Institute. There are free and paid for classes. And if you have a startup, please go to the booth downstairs with Scan and talk to them about our Inception program, where we can provide lots more support for you. I'm being thrown off now. So I just wanted to say one last thing. We're not there yet. We're not at artificial general intelligence. But if we are going to get there, this is very possibly the way that we will do it. Take a look at openmind.org. This is very, very profound work. Thank you very much.